Yeah, so now if you look at the second one, this shows the reduction of O2. And note that H plus is involved because we need the H plus because the H plus goes through that proton exchange membrane. So we can look at this one. We have 4H plus 4 electrons, and that produces 2H2O. Okay, so those 2 electrons, we just talked about the proton exchange membrane. Now, how much voltage is produced by a hydrogen fuel cell? So if you were to calculate E cell based on those 2 reactions you identified as the oxidation reduction reactions, what's going to be E cell? What's E cell?
1 positive. E cell is plus E.
Yeah, so we know that, let's see. E cell is equal to E oxidation, so that's going to be, we reverse the sign of this first one, so that's going to be, well, 0 volts still. Then for the reduction is 1.23 volts, so we add those two together. So E cell is going to equal, yeah, plus 1.23 volts. Now, what's going to be the source of hydrogen in a hydrogen fuel cell? So where does the hydrogen come from? Well, there's a very small amount of hydrogen in air, but it's so small you're not going to be able to extract it. Yeah, so one source could be from water, but it's actually very expensive to split water to make hydrogen. So although, and you did this in lab last week, when you split water, what is the minimum voltage required? Yeah, this is 1.23 volts. Now, 1.23 volts doesn't seem like a lot of voltage, but it actually is quite a bit of energy to split water. So it's actually too expensive to split water or to get hydrogen by splitting water. So what's another way to get hydrogen? Which acid?
Strong acid.
So you're saying you take an acid and do what with it?
Throw it in a tank.
Do what? So you take an acid and how? Now, if you take an acid, you want to reduce the acid. You reduce the H plus something else. So another way you can take a metal, for example, you take zinc metal. This reacts with HCl, and the product of this reaction is
zinc chloride.
Yeah, zinc chloride and yeah, this is one way to do. All of this isn't the way it's done. So one way to get hydrogen is actually by taking a hydrocarbon fuel such as methane. So you can take either methane, CH4, or ethanol. And the H2 is stripped from the methane or from the ethanol to make H2. Okay, so hydrogen gas can be produced that way. Now, what's one problem with producing H2 gas from methane or ethanol or methanol?
Still using fossil fuels.
Yep, still using fossil fuels. So that doesn't really curb our appetite for fossil fuels, and we're still taking hydrogen gas from fossil fuels. Okay, so that doesn't really work too well. Okay, so since you guys are the next generation of scientists and engineers, hopefully you'll come up with something on how to figure out cheap ways to imagine.
Would a materials engineer be a battery designer, or would it be?
Could be.
What engineering field is primarily in charge of design?
Well, materials science would be one because they're trying to figure out materials to make battery electrodes from. And actually, there's quite a bit of money, like the Obama administration early, a few years ago, devoted quite a bit of money into new battery technology. I think it was like a few $1 billion for research and Okay, let's keep on going. Okay, so here's some other information. This is about efficiency. So I found that when H2 is produced from the sun, for example, when H2 is produced from the sun, the quantum efficiency is 60%. So quantum efficiency tells you that for every photon, which is the energy in, okay, so for every 100 photons which go into this process, you get 60 electrons out of it. Okay, so that's what quantum efficiency 60% means. Now, photosynthesis has an efficiency of about 95%. Now, here's another one: splitting water with this Gore-Tex coated with these catalysts, PEDOT and PEG catalysts. That's another way to split water. Now, using organic photovoltaic cells, the efficiency is only 5%. So that means you're only getting 5 electrons out of every 100 photons which hit that photovoltaic cell. If you use an inorganic semiconductor photovoltaic cell, the efficiency improves to 10 or 15%. So again, this is another area of research to improve the efficiency of these PV cells. I love it.
When they say organic photovoltaic cell, are you talking some plant cells inside of?
Could be. But it's either that or they're using some sort of organic compound as a photovoltaic material. Okay, let's keep on going. And here's some information on the efficiency of energy devices. So again, when H2 gas is converted to electrical energy, for example, in a fuel cell, the efficiency is 80%. If it's used in a car, note that the electrical energy has to be converted to mechanical energy, so that motor inverter efficiency is 80%. So the total energy converting H2 to mechanical energy is 0.8 times 0.8, or is equal to 0.64 or 64%. Okay. The gas engine efficiency is about 20%. For a battery-powered electric car, where the efficiency is 90% for the battery and 80% for the inverter, so 0.9 times 0.8 is 0.72 or 72%. For a whole cycle electric car, the efficiency is 72%, so that's from up here. Charging the car is 90% efficient. A power plant using combustion, for example, burning natural gas, is 40% efficient. So if you combine these three together, 0.72 times 0.9 times 0.4, note that the total efficiency for an electric car is 26%, which is not much more efficient than a gasoline engine. So again, these are issues for you, since you guys are going to be the next generation of scientists and engineers.
What's the efficiency of a nuclear power plant?
We'll talk about that. It's starting last a little bit today, but we'll talk about that next week. Okay. And then the last part on electric chemistry is corrosion. So the cost of corrosion in the U.S. in 2002, a study was done, was $276 billion. This is 3% of our gross domestic product. For this year, it's estimated to be over $1 trillion, just the cost of corrosion. The worldwide annual cost of corrosion is $2.2 trillion. That's 3% of the world gross domestic product. So really corrosion is another area which economically is very important to either minimize or to solve because of these huge costs of dealing with corrosion. So for example, what's one way to prevent corrosion from occurring? Remember you did this in the Chem1A lab. Coat it with paint. That's one way. What's another way? Yeah, attach it to a more active metal. The more active metal is preference the oxidized over the less active metal. So that's called, the more active metal is called the sacrificial anode. What's another way to prevent corrosion? So you can coat the metal with a less active metal. For example, if you take iron and you put it in, what'll happen if you put iron? Okay, so let's say you have some iron bar and you put it in a solution of copper 2+ ion. What's going to happen? Yeah, so note that in this case here, you can coat the more active iron with the less active copper. And that's going to prevent the more active iron from corrosion. Okay, so those are just a few ways to prevent corrosion. I read recently that the U.S. military made the hull of a ship completely out of titanium, as opposed to steel. So what was the reason for using titanium rather than steel? It's lighter, it's stronger, and
It doesn't rust.
yeah, it's a lot less corrosion resistance. It's actually more corrosion resistant than steel. One problem with titanium though is 9 times more expensive than steel. So I'm figuring that since it's the U.S. military, that's actually our taxpayers' dollars, which is actually our money which made that titanium hull. Okay, this is the quiz we were supposed to take last week. This is the quiz we were supposed to take last week. We're not going to take this one today.
Sweet.
We'll take another one. Okay, so keep on going. So in Chem1A and Chem1B so far, we've talked about what we call regular chemistry reactions. Those regular chemical reactions involve electrons. So we know that the electrons occupy a large volume around the nucleus of the atom. When electronic transitions occur, that's how light is produced. That's electromagnetic radiation. The electrons are also responsible for bonding atoms together to make molecules. We know that when bonds break and form, a chemical reaction occurs. Then most chemical reactions release energy. In other words, most reactions are exothermic. Now, nuclear reactions are a little bit different. They involve the nucleus of the atom rather than the electrons. We know that the nucleus contains protons and neutrons in a very small space. And those neutrons and protons are held together by the strong nuclear force. The strong nuclear force is one of the 4 forces known in the universe. Do you know what the other 3 are? Yes, the electromagnetic force.
Gravity.
Gravity is the 3rd one, and the 4th one is...
Unified theory, so it's electroweak force.
Yeah, it's actually, yeah, so this is your hint, because if they call something the strong nuclear force, there must be a weak nuclear force. So it's just a weak nuclear force, which is the 4th one. Now, nuclear reactions produce particle radiation. So again, when you're looking at regular chemical reactions, they produce electromagnetic radiation. Nuclear reactions produce particle radiation. So the particle radiation include alpha particles or beta particles or neutrons. And nuclear reactions, which include fission reactions and fusion reactions, they produce a lot of energy. Really much more energy than a regular chemical reaction involves. Okay, so when I first started teaching Chem1B, I actually knew nothing about nuclear chemistry. So I was trying to figure out what's important about radiation. So anyway, what is radiation? What are the two types of radiation? Yeah, particle and, okay, we'll go back one slide.
Electromagnetic.
Yes, the two types of radiation are particle radiation and electromagnetic radiation. Okay, so here's some different types of radiation: alpha particles, beta particles, X-rays, gamma rays, neutrons, positrons. Now let's identify the radiation type first. So in other words, is it particle radiation or electromagnetic radiation? So what type of radiation are alpha particles? Yeah, particle. Okay, so note they're called alpha particles, not called alpha rays. What type of radiation are beta particles? Yeah, particle radiation. What about X-rays?
Electromagnetic.
Yeah, electromagnetic. What about gamma?
Electromagnetic.
Yeah, so note that gamma rays are a type of electromagnetic radiation. Okay, so you will see X-rays and gamma rays produced in a nuclear reaction, but it's actually not because of the nuclear reaction. It's actually because of something happening within the electrons and the atoms involved in that nuclear reaction. Then what about neutrons?